Before we do get to work on finding that relationship between electric field and electric potential, why don't we pause and do some electric potential examples? So first, let's do an example where we're finding the electric potential due to a single point charge. We're going to say that we have a point charge of 1 microcoulomb, which is placed at the origin in our picture. So this charge, I'm going to call that Q1. That's 1 microcoulomb. Part A, what is the potential at points A and B? Oh, first of all, we lost something in our picture. The distance from the origin to point A should be 0.750 centimeters. Oops. So the electric potential at point A and the electric potential at point B, that's the first thing we'd like to figure out. So at A, let's write down our relationship. Electric potential at point A, it's going to be K times our charge divided by the distance between point A and our charge. I'm going to call that RA. So R refers to the distance between your charge and your point. We can put in our numbers here, 8.99 times 10 to the 9 newtons meters squared over coulombs squared times our charge, 1 times 10 to the minus 6 coulombs, divided by our distance that's given in our diagram, 0.750, that was centimeters, so times 10 to the minus 2 meters, gives us an electric potential of 1.199 times 10 to the 6 volts. So there's my electric potential at point A. Notice I can't draw this. If this were an electric field problem, I would be drawing electric field vectors, but these aren't vectors, they're scalars, they're numbers. We don't draw those. At point B, my electric potential at point B is K times Q1 divided by RB. Whoops, Q1. RB is my distance between my charge and my point B. So this is my RB. Notice we have to do a little bit of math here to find RB. This is the hypotenuse of a right angle triangle. So RB is the square root of 0.750 centimeters squared plus 0.750 centimeters squared. Put that through the calculator, we get 1.0607 centimeters. So we've got 8.99 times 10 to the 9 newtons meters squared over coulombs squared times our charge, 1 microcoulomb, divided by our distance, 1.0607 times 10 to the minus 2 meters. And we get for this potential 8.476 times 10 to the 5 volts. This one's a little bit smaller, which we anticipated because point B is a little further away. Okay, there's part A done. What is the change in electric potential energy? So now this is talking about UE, since it's the change, delta UE, of a 2 nanocoulomb charge, which is moving from point A to point B. So now in this setup, I'm taking a new charge. I'm going to call this one QO. And I'm going to move it from A to B. So that's what my charge is doing. Part B, my change in electric potential energy, delta U, equals U at B, subtract U at A. That's my definition of a delta, of a change in. I remember that U of B is our charge times my potential at B, subtract my charge times my potential at A. So I'm using here the expression that potential energy is charge times potential. And my charge that I'm moving around is QO. Just make sure I put that in my equation. And if I wish, I can take my QO outside. VB minus VA. Okay, I know all these numbers. I can plug. Hang on, I just got to take the mic away and clear my throat. I am so sorry. It's very unpleasant to work when sick. Okay, let's try and put our numbers in. Hang on, I just have to pause the video.